this whole review, then you can go back on YouTube and look at it. So I'm going to first go through the review I put up on my Google site, and then we can go through any questions you guys may have. So yeah. Okay, so the first question says, if liquid nitrogen is presented like this, which one would best depict nitrogen after it boils? So we all know that nitrogen is a diatomic molecule, right? And so we can immediately, cross out answer choices A and B, because those are only one molecule next to each other. Like, it's not a compound of two. And so now we're looking at C and D. And so you're given this sample, and the question's asking after it boils. And boiling is going from a liquid to a gas. And so you're going to pick the choice that looks like it's in its gaseous phase. So which choice would that be? D. So does everyone see how I walked myself through that problem? That's basically what you guys should do when you see an ACS problem, because they're not going to be like the questions that you've seen on your test, where it was like clear cut, oh, it's showing this, so I can just pick this answer. You have to really walk yourself through the problem and walk yourself as to why it may be this. So number 1 is D. And the second question wants you to answer the following questions for the figure below. So we want to know if this reaction is exothermic or endothermic, and which step is the rate limiting step. So I'm just going to draw it real quick on my paper. Can everyone see that? Yeah? Let me zoom in a little. So this is what the graph looks like. So for exothermic processes, we know it's releasing energy. So if we're starting at a certain point and we're going to end here, so we start at, let's say, 5, and then now it's lower, so we know that it released energy, so this would be an exothermic process. In the second question, it was asking which step would be the rate limiting step. So what do we know about rate limiting steps? The rate limiting step is the slow step, correct. So if we know the rate limiting step is the slow step, rate limiting step equals slow step. What do we know about activation energies and the speed of a reaction? So the higher the activation energy, the what? The higher the activation energy, the slower the step would be, or the slower the process. Because it's going to take more energy to go over that little hump. So it's going to take more time to get over that hump. So the higher the activation energy, the slower the process. So we're going to look at which one has the higher maxima, and that would be B, the second step. Does anyone have any questions about this? No? Okay. Let's move. Yeah? You have a question? That's also chapter 13. So if you maybe don't remember much of chapter 13, I would reread that, because they love to put questions from chapter 13 on the ACS exam. And that even so, like, conceptual problems will also come from chapter 13. Number 3 says, which substance has dipole-dipole forces? So we have, let me just write them down. CCl4. So we're going to draw out every single one of them in order to figure out which one has dipole-dipole forces. So we have tetrachloride here. And the dipoles are going to face towards the more, what's the word? Thank you. More electronegative atom. That totally slipped my mind for a second. So it's going to go towards chlorine because it's closest to fluorine. And so since all the dipoles are facing outwards, they're going to cancel each other out. And this would be a nonpolar compound. And so therefore, it only has London dispersion forces. So that was answer choice A. And then we're going to draw out B, and that is NF3. And so it has 2 lone pairs at top, and then the 3 fluorines are going to be towards the bottom, and the dipole is going to be facing downwards. So here it is polar, and so therefore it has dipole-dipole and London dispersion forces. So the answer choice is B, but we should still check the other 2 just to make sure. So you have CS2, and that looks like this. It's a linear molecule, and the dipoles are going to face towards the sulfur. And therefore, they're going to cancel out, making this a nonpolar molecule. And then answer choice D is SO2, or SO3. And this has resonance, but it's always going to look like this, just at a different oxygen. So therefore, this one's also nonpolar as well, and these 2 will just only have London dispersion. You have a question? Why is it nonpolar? Because it's trigonoplanar. The shape of it has no lone pairs on the sulfur, but if you look at the shape of the molecule, since it's trigonoplanar, they're all going to cancel out. And this is chapter 11. So you guys can go back and reread this too, if you need a little freshen up. Are there any other questions? No? Okay, let's move on to the next one. Number 4 says, consider the phase diagram shown below. It says a sample of the substance in the phase diagram is initially at 175 degrees Celsius and 925 millimeter mercury. What phase transition occurs when pressure is decreased to 760 millimeters mercury at constant temperature? And so they give you the graph. So I'm just going to draw it out again on my paper. So this is 855 millimeter mercury, and this temperature is 145 degrees Celsius. And so the question was saying we initially start at 175 degrees Celsius and 925 millimeters mercury. So we're going to be somewhere around here. So we know this first part of the graph is a solid. And we know this part of the graph is going to be a liquid, and this part is a gas. So here we're starting off as a liquid. And then it says that the pressure was decreased to 760 millimeters mercury. So we started off here, and now we're going to go down to 760, so we're going to be right around here. So this is going from a liquid to a gas, and so what phase change is that? Excuse me? Good, vaporization or evaporation. So that's the answer choice you're going to pick. Are there any questions regarding this one? No? Okay, number 5 is asking which type of solid is dry ice, which is solid carbon dioxide, and they give you 4 choices, which are ionic, molecular, atomic, or none of the above, and the answer is molecular. And this is also at the end of chapter 11. So I would go back and reread those sections because those are questions they looked upon the ACS as well. They'll just give you an example of a molecule or a compound and then ask you which type of it is. Number 6 says, which process releases the greatest amount of heat? So the key word here is releases. So would that be endothermic or exothermic? Exothermic, great. So that was going to be an exothermic. So we're going to look at which choices are exothermic, and which ones would those be? So you're saying C, and what else? What'd you say? So I hear freezing, boiling, and melting. So it takes energy to break a bond. So if you have to break a bond, and you have to absorb energy to break it. So melting and boiling, you're breaking those bonds because you're going from either a solid to a liquid or liquid to a gas. So those processes would be endothermic. So melting and boiling are endothermic, and then freezing and condensation, therefore, would be the exothermic processes. And so now we have to compare, well, which one would be greater, condensation or freezing? And if you look at the delta H constant for delta H fusion or delta H vaporization, it's 6 versus 40.7, right? So it's going to take more, it's going to release way more when you are condensating versus if you're freezing something. So this is going back to that heating cooling curve, if you guys remember that, where it has like different plateaus, and the plateaus where phase changes. That's what this question is going off of. So you won't have to do that much math in ACS. I've heard there was like less than 5 on the last exam. So I'm trying to like prepare you to do problems that we used to do math to, but turn them to like a conceptual question. Is everyone okay with number 6? Yeah? Yeah, if you look at the different, because you know the equation for it is Q equals N delta H. So now we're going to compare the 2 delta H's. And you know the delta H of fusion is only around 6 versus the delta H of vaporization is 40. So if you look at that number, you can see, oh, well, this is going to be way more. It's going to release way more heat or energy than the fusion one. Okay, number 7 says, which compound do you expect to be soluble in octane, which is CaH18? So they gave us 4 answer choices. I'm going to write them down on my paper. So we have CaH18. This is another problem where I would advise you to draw out the compounds. So CaH18, we know that this is a hydrocarbon. It's covalent, and so it's nonpolar, and it only has London dispersion forces. And so since this question is talking about solubility, we know that like dissolves like. So we're going to look for the one that is most like octane. And so octane only has London dispersion forces. So we're going to look for the molecule or the compound that only has London dispersion forces. So looking at A, CH3OH, we have this. Automatically, we see there's a hydrogen automatically bonded to a oxygen that's bonded to a carbon. So right here, there is hydrogen bonding. And hydrogen bonding exists between nitrogen, oxygen, and fluorines. And then also, this is a polar molecule because you have all of these dipoles facing towards the carbon, but then you have this one facing towards oxygen. So there's a little dipole moment here. So this is also polar. So if it has hydrogen bonding, we know that it is dipole-dipole. And we also know that it has London dispersion forces. And also, every molecule and every compound has London dispersion forces. Now we go on to B, which is CBr4. And so the dipoles are going to face towards the bromine, because that's the more electronegative atom. And so all the dipoles are going to cancel out, making this a nonpolar molecule, and therefore only having London dispersion forces. I'm just going to draw out the other two. So we have H2O. And H2O is a bent molecule. It's polar. It has hydrogen bonding, dipole-dipole, and London dispersion forces. And then also NH3 looks like this. And it has a dipole going up. So this is polar. And it's a nitrogen directly bonded to a hydrogen. So this also has hydrogen bonding, dipole-dipole, and LDF. So answer choice B was the only one that only had London dispersion forces. And so since octane only has London dispersion forces, and that one only has London dispersion forces, that one's going to be the most soluble in octane. Is everyone okay with this? Yes? Okay. Number 8 says an aqueous solution is saturated in both potassium chlorate and carbon dioxide gas at room temperature. And we want to know what happens when the solution is warmed to 85 degrees Celsius. Well, we know from chapter 12 that as we increase temperature, gases tend to evaporate out of solution. So since we know CO2 is a gas and we have carbon dioxide in the aqueous solution, then if we're going to warm up that solution, that's going to come out. But potassium chlorate will just stay in the solution. So nothing's going to happen to that. So the answer choice that is correct would be B. Carbon dioxide bubbles out of solution. And I'm pretty sure she's done this question as a clicker question earlier in the year. So if you go back through those slides, you can see that too. Number 9 says, which of these aqueous solutions has the highest boiling point? So we know boiling point is a colligative property. So there's boiling point elevation as one of them, freezing point depression, vapor pressure lowering, and osmotic pressure. So you should really know those 4 colligative properties because they will be asked on the ACS exam. So I'm going to write our answer choices down on paper. So we have So boiling point and it's a colligative property, and we know there is a equation that goes along with it, and that's the change in temperature of boiling equals the Van Hoff factor times molality times the boiling point constant. But since this is all dissolved in the same solution, it's an aqueous solution, so it's all dissolved in water, we can ignore the Kb because the Kb is going with the solvent, and all other solvents are going to be the same. So we're going to ignore the Kb in this question. And now we're looking at the molality. All of the molalities are the same, so we can essentially ignore that too. So now we just want to look at the Van Hoff factor. And the Van Hoff factor goes off of how many ions, or how much does the actual compound dissociate. So that's thinking of, which one is nonpolar, which one's ionic, which one's covalent, stuff like that. So we know C6H12O6, glucose, is a nonpolar molecule. It's covalent, so it's not going to dissociate into anything. Or it is, but it's not going to break apart any further. So its Van Hoff factor is going to be 1. And we know KNO3 is ionic. It's also a salt, so this will break into K plus and NO3 minus. And you need to remember that NO3 is a polyatomic ion. So it's not going to break up any further because that's how it is. And you know that the charge is -1. There's a little trick called NSP123, but you guys don't really need to go that into it. As long as you know that this K is +1, then this NO3 would be -1. And you can find that on the periodic table. So you have K plus and NO3 minus, and so the I will equal 2 because it breaks into 2 different ions. And now the last one is calcium nitrate. So we know this breaks into Ca2 plus and NO3 minus. But there's two nitrates, so we're going to put a 2 in front of there. So now it's not just 2, the I is going to be 3. So which one would have the highest, what was the question? The highest boiling point? C, great. Because this I it's the biggest I, it has the biggest Van Hoff factor, so the answer should be C. Are there any questions regarding this one? Okay. The next question says, what is the scattering of light by a colloidal dispersion? And so we know that as soon as you see colloidal dispersion, you know that's the Tyndall effect. That's from chapter 12. If not your quiz, there was a quiz question or it was a test question. And it should be in her PowerPoint if you haven't seen this one. But it's also at the end of the chapter 12. I know that for a fact. Okay, number 11 says a solution is an equimolar mixture of 2 volatile components, A and B. Pure A has a vapor pressure of 50 torr, and pure B has a vapor pressure of 100 torr. The vapor pressure of the mixture is 85 torr. So what can you conclude about the relative strength of the intermolecular forces between particles A and B relative to those between particles of A and between particles of B? So, does anyone have any idea for this question? The answer choices are, the first one says the intermolecular forces between particles A and B are weaker than those between particles of A and those between particles of B. The answer choice B says the intermolecular forces between particles A and B are stronger than those between particles of A and those between particles of B, or that those forces between all of them would be the same. So looking at it, we have pure A is 50 torr and pure B is 100 torr. but the mixture is 85 torr. So the intermolecular forces between particles A and B are going to be weaker than those between particles of A and those between particles of B, because pure B's vapor pressure is higher than the mixture. And normally, you know, the colligative property of vapor pressure is vapor pressure lowering. So that's why the mixture is a smaller value. The answer should be A. And this is also, this question's from your book at the end of the chapter. If the intermolecular forces between particles A and B are stronger than those between A and those between B, I would say the vapor pressure of the mixture would be higher, because those are so strong, the intermolecular forces between A and B are so strong that they're not going to, what's it called? In a mixture, they're going to be so strong that they're not going to want to break apart, you know, because it's vapor pressure. It's evaporating. So I'd say it would have to be larger. Okay, number 12 says this is a sample of a first order reaction, and they want to know which one will show the sample after 2 half-lives. Where's the other one? Okay, the last one is there's just 2 dots in the square. So we know that a first order reaction is independent of its concentration. So first order half-lives are independent of concentration of the reactants. So if that's the case, and in that box you counted that there was 8 dots there. So we started off with a concentration of 8 molar, then after its first half-life, the box should then have 4 of them in there, or the concentration of it would be 4 molar. Then after the second half-life, so you'll divide the 4 by 2, then it should have 2 dots in the box, and therefore the concentration would therefore be 2 molar. So this is only first order reactions where it's independent of its concentration. And that equation is 0.693 divided by K. Don't quote me. It's in the book, but I know 0.693 is in there. But that's a really key thing to note, that the half-lives are independent of the concentration for first order, because they will ask a question in some form or fashion about this. But this one, I just want to show you guys in a visual format what they could ask you. So you need to be able to look at what it was given to you and compare it to those, but also taking account the knowledge that you know about first order reactions and concentration. So if this one had 8, the first half-life would have 4, so B would be if it was just 1 half-life, and so therefore D would be 2 half-lives. The answer is D. Are there any questions? No? Okay. Number 13 is a kinetics problem. It says, for the reaction 2A plus B yields C, the initial rate was measured at several different reactant concentrations. From the tabulated data, determine the rate law for the reaction. So we know that we cannot ever determine the order of reaction without doing math or without doing an experiment. You cannot just look at a reaction and be like, oh, well, this has a coefficient of 2, so the order of A must be 2. You cannot do that. You have to do it experimentally. And that was also a question on one of y'all's tests where I think she just asked, how do you find the order of the reaction for a reaction? How do you find the order? And it was, you have to find it experimentally. So this would be what happens if you find it experimentally. If you guys have done the Chem 2 lab, you would have done an experiment like this where you had to do this math. And so for this one, I'm gonna first try and find the concentration of A. Does everyone have that table written down somewhere? Or somewhere they can access? Yeah? Okay, so I'm gonna switch it over. So I took trial 2 over trial 1 because for the concentration of B, they were the same. So I'm going to pick the one where they're the same so I can solve for the order of A. And so now I'm going to put the 0.10 over the 0.05 because that's going to be the larger value, and it's easier to do the math that way. But you can do it the other way. It's more so your preference. So I did 0.10 divided by 0.05, and then raised that to the m. And then I did 0.05 divided by 0.05, raised it to the n, and then equaled it to the initial rates that were given for those trials. And make sure you still keep the same trial all the way through, because a common mistake is to do all of this and then put 0.035 on the top, and therefore your answer would be wrong. So just make sure that you are staying through the whole way, and just keep checking yourself. So after you set up this way, you solve, and this will cancel out because this will just be 1, so it can be ignored. And then here you'll get 2 to the m equals 2. And so 2 to the what equals 2, that would be 1. So the order of A would be first order. And now we have to find the order of B. But if you look back to our tabulated data, there was never a trial for A where they were two trials where they were the same. So we're going to use what we got from this first one. So we knew that the order was first order here. So we're going to take trials. I took trial 3 and trial 2. So I put 3 on top, 2 on the bottom. So I had 0.2 divided by 0.1 raised to the first order, which is what we got from here. Then I did 0.10 over 0.05, raised that to the n, and then equal that from trial 3 over trial 2 initial rates. And then when you solve that, you'll get 2 times 2 to the n equals 8. Well, now here you would just divide this 2 from here, and so you'll have 2 to the n equals 4, and then you'll be able to solve for the order of the reaction, or the order of B, which would be n equals 2. And so when you go to write your rate law, it would look like this. Rate equals K of the concentration of A times the concentration of B squared. What would be the order of the overall reaction? 3. So the order of the whole reaction would be 3. And you do that by you're adding this order from A and this order of B. So you add those together, you'll be able to find the order of the overall reaction. So that can be another question that they ask you. Excuse me? When it was 2 raised to the n here? Yeah, I divided this 2 from, I took this 2 and put it over here because we're trying to solve for just 2 to the n. I was trying to figure out, well, what to the, 2 to the what will equal 4? And that would be 2. Are there any other questions? No? Okay, 14 says, at around what time does the reaction reach dynamic equilibrium? Does anyone have a guess? you would guess? Excuse me? 2 minutes? They're not all quite at the same, they're not all quite leveled. So when you look at this and you want to know at what time does it reach dynamic equilibrium, we're going to see what time do they all plateau at the same time. So at 2 minutes, they're not quite all plateauing at the same time. Yes, at 2 minutes, they start to intersect lines, but when you're looking at this question, you want to look at what time do they all start to plateau. And that would be around like 3 minutes. And this is a very popular question on the ACS exam. They don't ask it in your book, but there is a part in the book where it briefly discusses this diagram. Are there any questions regarding this? No? Okay. So the answer was C. Okay, number 15 says, given the reaction of methanol yielding carbon monoxide and 2 hydrogen gases, if the equilibrium concentration of carbon monoxide and hydrogen gas are greater than the equilibrium concentration of methanol, is the forward or the reverse reaction favored? I'm just going to rewrite it here. So if you're going to do a K expression, you're going to put carbon monoxide on top with hydrogen gas raised to 2 because that is the coefficient of hydrogen gas. And when you're doing the K expressions, it's always going to be products over the reactants. And so that's why methanol is on the bottom. And so if the question said that the equilibrium concentrations of carbon monoxide and hydrogen gas are greater than the equilibrium concentration of methanol. So this is a greater value than down here. So the products are greater than the reactants. Therefore, the forward reaction is favored, and K would be much greater than 1. So those are 2 things to look at. So if K is much greater than 1, the forward reaction is favored. Or if the products are greater than the reactants, then the forward reaction is favored. So it would be great to memorize both of them and think about it, both of them, because the question could be asked pretty much any way. Are there any questions regarding this one? Excuse me? Yeah, so let's say that this whole equilibrium is, or the equilibrium concentrations up top are 5. And the bottom is 1. 5 over 1, that K equals 5, and so 5 is much greater than the value 1. So that way the forward reaction is favored. Now, if this bottom one was greater, so this was 5 at the bottom, and this is 1, so now you have 1 to the 5th, and that's way smaller than 1. So therefore, the reactants would be favored. Does that make sense? Yeah? Okay. Let's move on to the next question. So next question says, what is the correct expression for the equilibrium constant Kc for the reaction between carbon and hydrogen gas to methane shown here? And so we have a solid and 2 gases. So what 2 phases do we not put in our Kc expression? Great, so we're not going to include solids and liquids in our K equilibrium expressions. So we can just ignore carbon. But we have CH4 as a product. It doesn't have any coefficients in front of it, so it's not going to be raised to anything. And then we have hydrogen gas, and it has 2 coefficients. It has the 2 as a coefficient in front of it, so that's going to be raised to 2. So therefore, the answer should be what? D. Great, because carbon is not included, and it has the right exponents. Okay, so this one says the decomposition of NH4HS is endothermic, and they give you the reaction here, and so they want to know which change to an equilibrium mixture of this reaction will result in the formation of more hydrogen sulfide. So I drew it out right here. So the choices were either a decrease in the volume of the reaction vessel at constant temperature, an increase in the amount of NH4HS in the reaction vessel, an increase in temperature, or all of the above. So if we were to, they want to say which one of those would result in the formation of more H2S. So the first choice says a decrease in the volume of the reaction vessel at constant temperature. Well, if you're decreasing the volume, then it's going to want to go to the side with less gaseous moles, or less moles, period. So it's not going to be that one, because that one would not result in this becoming more. But this is also an endothermic process, so that's why I put heat on this side. If it was exothermic, I would put heat on the product side, like as a placeholder and for me to think about it. And so the answer choice B says an increase in the amount of NH4HS in the reaction vessel. Well, that's a solid. So the solids are not going to have an effect of this in regards to Le Chatelier's principle, because that's what this is. It's not going to have an effect, so B is not going to be the answer choice. So now let's look at C. C says an increase in temperature. Well, if we have heat on this side because it's endothermic, and we're adding more heat to this side, then the other side's going to want to balance out that seesaw. So therefore, the H2S will increase if we increase the temperature. Does everyone see that? Yeah? Why it's not A? So it says a decrease in the volume of the reaction vessel at constant temperature. So if we're going to decrease the volume, it's going to be becoming smaller, and you want to go to the side with less moles of gas. Well, this has 2 moles of gas, and this one only has solid. So this one's like a question where we can't even ask in this state, because this is a solid. That choice was C. Number 18 says, what is the effect of adding helium gas at constant volume to an equilibrium mixture of the reaction? Of carbon monoxide plus chlorine at equilibrium with COCl2. Well, helium gas is not even in this reaction, so it's not going to have any effect on it. So the answer choice would be C. The reaction is not going to shift in either direction because helium is not even part of it. So you add helium, nothing's going to happen. Number 19 says, determine the pH of a 0.188 molar NH3 solution at 25 degrees Celsius, and the Kb of ammonia is 1.76 times 10 to the negative 5. So this is an ice table question. The minute you see pH and they give you a Kb, just think ice table. And this would be probably one of the math problems they would ask you. So first you're going to write out the equation. So you're going to have ammonia in water at equilibrium with NH4 plus and hydroxide. They give you the Kb, so that's another hint that this is a basic solution, and therefore it would produce hydroxide. So now you can write the ice table, and they gave you an initial concentration of 0.188 for ammonia. So therefore, if they only give you that, then you can assume that the other two are 0 initially. And then we do not have any equilibrium concentrations, so we're just going to use X. So you're going to have minus X for the reactants and plus X for the products. And since they all have one coefficient, there is not going to be any coefficients or any number in change of X. It's just going to be negative X plus X and plus X. And then for equilibrium, we're going to have 0.188 minus X for ammonia, X for NH4 plus, and X for hydroxide. And the K expression, the Kb expression would be NH4 plus times the hydroxide concentration all over NH3. And how come we do not include water? Because it's a liquid. So water will not be included in this expression, or also in our ice table for that matter. And so we know the Kb that was given the problem was 1.76 times 10 to the negative 5. So we're going to set that equal to what we have from our ice table. So we're going to have x squared on top and then 0.188 minus x. Since this is raised to negative 5 and that's greater than negative 3, because negative 3 is like my spot where I would stop. And if it's anything from negative 3 and lower, or like negative 2, negative 1, I would do a quadratics, and I would use x, this x right here. But since this is negative 5, we can assume that this x is small or negligible, so I'm just going to cross this one out. You're not going to cross this one out because you need that variable. It's just when it's in parentheses. And so you're going to get x equals 0.001819 molar. And if you go back through your ice table, that's that concentration for NH4 plus and hydroxide. And so we can solve from the pH with the hydroxide concentration. So if you take the negative log of hydroxide concentration, you'll get the pOH. And so you get the pOH to be 2.74. Now you know that 14 minus the pOH will give you the pH. So if you do 14 minus 2.74, you'll get 11.26 as its pH. Which makes sense because it's greater than 7, it's basic, and that's what we are dealing with in this problem. So the answer choice for this would be D. Are there any questions regarding this one? No? Okay, well, let's switch back. So the next question says, identify the conjugate base in the reaction shown here. So we have HClO2 aqueous plus water aqueous at equilibrium with hydronium ion aqueous and ClO2 minus aqueous. So we want to know which one would be the conjugate base. So that has to go with the acid. And what do we know acids do? Excuse me? Yeah, good. They donate a hydrogen. So we're going to look at which one's donating the hydrogen. And that looks like HClO2. So HClO2 is going to donate this hydrogen, and that's why it's left with ClO2 minus. So here would be the acid making ClO2 minus the conjugate base. And we can also, don't forget to note that H2O is an amphoteric solution or compound, and so it can act as either an acid or a base. So in this problem, it's acting as a base, but other times it can act as an acid, like in the problem we just did earlier with NH3 plus H2O. there it was acting as an acid. So the answer choice for 20, the correct answer is D. Number 21 asks, which graph shows a titration of a strong acid and a strong base? Well, A is a really smooth S. So this one's going to be a weak acid and a strong base. Answer choice B has two humps. So this is actually going to be a diprotic acid. That's what the graph would look like. But it's not so much going to be a strong acid and a strong base titration. But if you look at answer choice C, that's a really strong and sharp S. So C would be the answer for a strong acid and strong base. And then D would be a strong base and a weak acid, or excuse me, it would be a weak base and a strong acid. So make sure you guys are familiar with these graphs, because these are another popular question. Are there any questions regarding this? No? Okay, number 22 says, an ideal buffer contains what? Significant amounts of both a weak acid and its conjugate base. B says small amounts of both a weak acid and its conjugate base. D says small amounts of both a strong acid and a strong base. Or E, significant amounts of both a weak acid and a strong base. And so this one would be A, significant amounts of both a weak acid and its conjugate base. Yeah, A is the answer. And that's also in your book, and I think this is also from one of y'all's tests. Okay. Okay, number 23 says the sign of delta H reaction and delta S reaction for several different reactions are given. In which case is the reaction spontaneous at all temperatures? Well, we know it tends to be spontaneous when it's an exothermic reaction. So that would be when the delta H reaction is negative or when it's less than 0. And also it tends to be spontaneous when the delta S reaction is positive or greater than 0. So if it's both exothermic and the entropy is positive, then it's going to tend to be spontaneous at all temperatures. And so the answer should be C. That's one way to think about it. Another way is if you just remember that chart that is in your book. Okay, number 24 says, which process results in an increase in entropy of the universe? And so you have for answer choice A, the cooling of a hot cup of coffee in room temperature air. So this will happen on its own, and so this is a spontaneous process. B says the evaporation of water from a desk at room temperature. This is something else that would happen on its own. So you can say this is a spontaneous process as well. And also the melting of snow above 0 degrees Celsius. Well, 0 degrees Celsius is when water freezes. So anything above it, it will melt. And so therefore that is also a spontaneous process. And the answer should be D, all of the above. the melting of snow is the evaporation of water from dust. Yeah, it's an endothermic process, but but it will happen on its own. So that's where you can say that it's spontaneous. It won't happen at any temperature, and that's where the endothermic comes in. This is where the delta G, it would be spontaneous at some temperatures and non-spontaneous at others. But we're talking about the entropy of the universe. So entropy is delta S. So, excuse me? Yeah, if we were putting in not only entropy and enthalpy, then they'll be talking about delta G. But entropy is specifically for delta S. Okay, number 25 says, which statement is true for the freezing liquid water below 0 degrees Celsius? So what would you guys think the delta H would be for something that is for the liquid water that's freezing below 0 degrees Celsius? What would delta H be? Excuse me? Negative? Good. So the delta H would be negative. What about the delta S? Negative. Why do you say that? It's freezing. So it's going from a liquid phase to a solid phase. So the entropy is going to be decreasing. And so therefore the delta S would be negative. Great. And then what about the delta G? Why do you say negative? Good. So delta H and delta S are both negative, but if you go back to the chart, if they're the same, are there any restrictions in temperature? At low temperatures, it will be spontaneous. And so delta H is negative. If delta H is negative, then it's spontaneous. And therefore, 0 degrees is a low temperature to me. So this one would be spontaneous at low temperatures, and that's why the answer choice is B. So you see how we walked ourselves through this question? This is something I would want you guys to do in the ACS. Don't just, well, this looks right, I'm just going to mark this. No, actually walk yourself through the answer. Okay, number 26 says a reaction has delta H reaction as negative 255 kilojoules and delta S reaction as 211 joules per Kelvin, and I want you to calculate the delta G reaction at 55 degrees Celsius. So we have the delta H, that's in kilojoules, and the delta S is in joules. Well, the answer choices are in kilojoules, so we're going to change the delta S from joules to kilojoules as well. And so when you do that, you divide by 1,000 joules, and you'll get 0.211 kilojoules. And then the temperature is in Celsius, but in that equation, that is delta G equals delta H minus T delta S, we need the temperature to be in Kelvin. And so you're going to add 273 plus 55 to get 328 Kelvin. And then you're able to plug it into that equation. So you get negative 255 kilojoules minus 328 times 0.211 kilojoules. And then in the end, your answer should be negative 324 kilojoules, or answer choice D. Are there any questions regarding this one? No? Okay. Okay, I'm going to switch back to the computer. Okay, number 27 says, which statement is true for voltaic cells? So A, electrons flow from the anode to the cathode. B, electrons flow from the more negatively charged electrode to the more positively charged electrode. C, electrons flow from higher potential energy to lower potential energy. Or D, all of the above. D, all of the above, is that everyone saying that? Yep. Okay. So number 27 will be D. -26 was negative 324 kilojoules, so D. Okay, number 28 wants you to calculate the cell potential for the following reaction that takes place in an electrochemical cell at 25 degrees Celsius. So they gave you this question in cell notation. And so we have SN solid, and you have AG solid. So those two would be the metals in that beaker. And then you have SN2 plus and AG plus, and then you have the double lines right here. And those double lines are representing the salt bridge. And you know the ions will flow directly through the salt bridge. And so that's why those ions are right next to the salt bridge. So that's another way of remembering it. And if they were to ask you to write something out in cell notation, you will be able to do that. So this question has to do with concentrations. And so we're going to need the what equation? Which equation would we use for this one? Okay, that's a good idea, but this one has concentrations in it. So we have to take those in consideration. So there's the Nernst equation. So you have E cell equal to the standard E cell minus 0.0592 volts over N times log of Q. So we're going to do this problem together. And I'm going to write out what we have here. So we have SN solid, SN2 plus, okay, I'm going to switch it over. If you look in your book, or also the ECS is going to give you that list of the tabulated values, or they'll put it in the question. So, excuse me? The log Q? Is that what you're asking? Yeah, it should be this equation. E cell equals standard E cell minus 0.0592 volts over N log Q. So we're going to need the half reactions for this one. So you're going to look on your table of values, and we're looking for the SN2 plus. So you have SN2 plus aqueous plus 2 electrons yields SN solid, and that's negative 0.14 volts. And then we're going to look for silver. And so you have Ag plus an electron yields Ag solid. Okay, what else can we find out from the cell notation? Great, so we can figure out which one's the cathode and which one's the anode just from looking at what was given from a cell notation. This is 0.80 volts plus. Okay, so we know right here is the anode, and what happens at the anode? Excuse me? Great, yeah, so it's going to move from the anode to the cathode, and also that there's oxidation happening at the anode. So if you think of an ox, so anode oxidation, and this one would be red cat, so reduction at the cathode. So this is the cathode. A reduction's happening here. So what would be the, it's negative 0.14. Sorry, I have really bad handwriting. And then 0.80. Okay, so we can figure out N. And N is the moles of electrons that are being shared or transferred in this reaction. And so what would N be? 2. Great. So N would be 2 because this one has the most, and that is 2 electrons. And we can just multiply this reaction to 2 if we need to get that overall reaction. But this question's not asking for the overall reaction, so we can just note that, N is going to be 2. And how can we solve for the E standardized cell? Great, so E cat minus E an. And so we're going to take, which one's the cathode again? Great, so I'm going to write cathode here and anode here. So the cathode one would be plus 0.80 volts minus negative 0.14 volts. And what do you guys get for E standardized cell? 0.54, 0.94 volts. So now we have N equals 2. We have the E standardized cell is 0.94. And so now we can, we can put this in the equation. So we have E cell equals 0.94 minus 0.0592 volts over 2 times log of Q. And so we need to know which one's going to be the products and which one's the reactants. Well, anode is oxidation. Oxidation loses electrons. So this reaction is actually reversed. So it's actually going to be Sn solid yields Sn2 plus 2 electrons. Because for oxidation, they're losing electrons, so we're going to want to put that in the product side of the reaction. So if this one's reversed and we have Sn2 plus now as a product, and we know for Q and K, you're going to put the products over the reactants. So we're going to have the concentration of Sn2 plus, so 0.022 molar, over the concentration of Ag plus, which is 2.7 molar. And then you're going to plug all of that in your calculator, and you'll be able to get the E cell. And you should get plus 1.01 volts, which is A. Are there any questions regarding this one? All right. I'm going to switch back to the computer. So we're on our last question for my review. It says, use the standard half cell potentials listed below to calculate the standard cell potential for the following reaction occurring in an electrochemical cell at 25 degrees Celsius. So they give you the reaction, and we don't have to write one out. But this is also from the question we just did. So you have Sn solid plus 2Ag plus aqueous yields Sn2 plus 2Ag solid. And so we already solved for this in the last question, which was E cell equals E cat minus E an. And we already determined which one's the anode, which one's the cathode. So we should already have this answer. Is everyone okay with that? Yes? And we got the answer to be B plus 0.94. I wanted to show you what an ACS question will look like. So they would have a figure, and they'll have you answer the question based off the figure, and then they'll also have just a bunch of conceptual questions. So this is why I'm really stressing that you guys reread all of those chapters. I know it may be boring, but if you read and understand this, if you read and understand all of those chapters and all the conceptual parts of that chapter, like you can, if you're strong with the math, I would say skip the math for now. Just go through the book and just read all the concepts, take a little notes, think of what they could ask you or what they may ask you, and then make a little outline on a sheet of paper and just study those, because when you get to this, you'll be looking at your test and you just fly through those problems, and then you'll have more time to work through the problems that may require more work or questions that may require you to think a little extra about the question. So the carbon dioxide question, you see how I put that in there, and it happened to be in one of their review books. So really, that would be one thing I would look at, is the different examples for ionic, molecular, metallic, etc. And don't forget to go through, where is it? Don't forget to go through chapter 19. There would be questions like this. I didn't find any in the back of the book that I liked, or the back of this chapter that I liked, but if you go through the examples of chapter 19, just really go through right here. So example 19.1, I would go through that example, and example 19.2, and maybe example 19.3, and also example 19.4. I would go through those 4 examples, and you should be okay with chapter 19. Like I said, the back of the book I didn't find, or the back of that chapter where it was like, where is it? These, I didn't like those questions, but I would go and like Google ACS questions regarding chapter 19. So if you want to do extra like practice on those, I would go and look for those online. Do you guys have any specific questions you want to ask me? Yeah.
So on the ACS exam, will they give us the equations right now, like, or so if it's saying hydrogen and something bond together, is it going to write that out for us like she does on exams, or do you have to just know how to do that?
I wouldn't count on it. I would really know, I would want you guys to know how to write those out.
Yeah.
I tend to, like, on my reviews, I tend to just have it, like, said so you guys can get the practice of writing it out. Yeah, don't depend on that.
Okay.
And also, you probably won't get a heating cooling curve question, but, like, constants like that, the ACS doesn't, they usually don't put it in there. What you guys have been using for your test, at the end of the test, that's just basically what they give you.
Yeah. The new review book that they put out, it didn't have any of the equations that the sheets we've been using on the test. It just had a periodic table, and it just had like.
Then I would say they probably took out a lot of math. That would be my guess. They took out a lot of the math questions because so in that used to come to my tutoring sessions last semester. She gave me like a list of ideas that she remembers, and she said that there wasn't that many math problems.
Yeah, because they completely took out any of the equations. There's no nurse.
Yeah, so I would say don't focus too much on the math. If you reach math, it may be like, it would be the pH question. You know how to do that. And what you just did, you already know how to do that. So really focus on the concepts and understanding Chem 2. If you can understand Chem 2, you will get through the ACS, no problem. Yes? Number 2, part B. That was that kinetic problem, right? So it was which one's the rate limiting step? So activation energy, the higher the activation energy, the slower the step. So the higher the maxima, the slower the step. So the answer choice, or the answer would be B. The second step would be the rate limiting step. Yeah? Yeah, they changed the ACS from when I took it. Now it's only Chem 2. Mm-hmm. Any other questions? Yes? Number 8. Number 8. It's B. Carbon dioxide bubbles out of solution. Any other questions? Any other concerns? Are you guys ready for the test? Do you feel confident? Yes? I really don't stress about it. The ACS it's different. I can say that. It's a different type of test. It's a standardized test. If you took AP Chem, it looks just like the AP Chem test. I can't hear you. To get the edge length of unit cell, I don't think you would calculate it. I would still just refresh your mind or your memory about it. They would ask you questions about they could ask you how many atoms are in that. So yes, I would go back through that section and try to remember that little chart there, because they're not going to give you the chart like she did. Mm-hmm. How would you calculate or not calculate? So let me go back through the book. So that was chapter 11. So here, you're asking? How would you calculate R? The length? Okay, so that's something, if you can just remember if you remember the chart, you can remember L equals that, and then they'll give you the radius and you just plug it in. But questions that they would ask would be what's the coordination number for a simple cubic? They would really want you to know this chart. So I would go back and try to remember the chart as well. Yeah?
Is it curved or just what we get out of
From what she said in class, she said that it's not curved, but there's questions that she feels that we didn't go over and you weren't ready for, and so it's adjusted. Not so much a curve. Any other questions? Really know your intermolecular forces, know your colligative properties. Titrations, I would say, understand how a titration works. Just if you have the lab, then you know. Also, if you want, you can YouTube an example of a titration, just so you understand how it works, because they could ask you questions regarding that. But I don't know what y'all's test is going to look like, because I took it with both Chem 1 and Chem 2, so it was way different for me. But honestly, do not stress. If you have any questions, I'm here. And Dr. Hashim is there if you guys have her email. Thank you guys for coming. I really appreciate it.